Hello everyone. Uh, I welcome you to the last session of this course. Uh, so let's get started. It's around 7:01. Um, maybe we will start with some questions. If you have any questions regarding previous assignments or lecture notes, you can ask now. Uh, Once your doubts are cleared, what we will do is we will go through the course content again quickly to revisit.
So good evening.
Yes, Sir.
Sir, actually, I had a doubt in that quick scheme. Sir, in the week 5, I guess, yes, week 5, and that time integration method.
What was the
So
question in week 5 assignment?
no, sir, actually, sir, I didn't understood means like that quick scheme and that time integration method means it was a little bit confusing for me.
Okay,
So,
okay, okay, okay. So, yeah, so let me tell you that quickly. Um, so, uh, your doubt is in quick scheme, right? So, what do you understand by quick scheme till now? So, it would be helpful for me to explain it to you easily.
yes, sir.
What do you understand by quick scheme? Do you have any idea?
Sir, actually, I fully understood those four schemes which were before this.
Okay.
In this quick scheme, I guess there was it's a uh, it's like a hybrid scheme between the hybrid scheme and that upwind scheme. So that only I understood. Then after that,
Right.
I didn't
So,
get.
let me tell you. So, let's say in finite volume method, okay. Uh, Finite volume, we always draw a volume, right? So, this is our present cell where we need to find the which is our interest, okay. So, this would cell, this would be west cell, and this would be west of west, okay, and the west face. This is the east. So this is east face, this is west face. So this lowercase letters are actually represents faces, okay, and cell centers are with capital letters. So if you say you know what is quicksand, so usually in a finite volume formulation we need to find the fluxes crossing the faces, right? Let's say if you have a pi by dou x times dot dA is equal to 0. So which is nothing but a diffusion equation, right, in integral form. So let's say if you want to find if you discretize it, it will be like gamma into dou phi by dou x at east face minus gamma into dou phi by dou x at west face. So you need to find the fluxes at west. So west and east faces. So we don't know. We store the values at the cell centers, right? So here, and here only we will store the values. So what we do is we apply these schemes to get the phase values. Okay. Let's say for east, if you are getting from the phase value, uh, what we actually do is we will write it in terms of function of phi p, phi east, and then phi west. So what we did was we selected these three points for this interface to find for this phase, to find the value at this phase. We took 3 points which we took 1 point on that side and 2 points on this side. So actually it is based on the flow. Okay, so as you said, this quick scheme is actually a hybrid scheme, actually a hybrid scheme for upwind and central. Okay, so it is a hybrid of upwind and central. We know what is upwind. So let's say the flow velocity is like this. Upwind means to find this velocity we will take p value and w value. So if you take more and more in the upwind direction, then it is called upwind approximation, right? So here if you take these two, then it becomes upwind, and if it's a central differencing, you will take p and e, right? So in quick scheme what we do is we just take both upwind direction and one central differencing in the downwind direction. So it's actually a hybrid for upwind and central, and we write this in terms of p present, east and west. Okay, so for a phase we need these three values to find the flux at the phase. So that is how it is done. All others are just derivations. So you can check different books for derivation. So how are we getting those coefficients 3 by 4 or something like that? Coefficients are there, right? So those coefficients are obtained from derivations. Yes, Hussein.
Sir, actually, as you said that it's a hybrid scheme, it's like between the upwind center.
Right,
Okay, sir, and that we have to find the functions also, that phi p, phi e, and phi w, right?
right.
Sir, but means like there was some range about that 0 to 10 Peclet number should be there. Means like if 0 to 10, then we can if it's about 10, though then we can consider that diffusive flux is 0, right? So sir,
Right.
what was that part? Means
So
uh,
actually, so what is Peclet number? You know that Peclet number, right? So this
yes
Peclet
sir.
number is actually convective flux by diffusion flux. So if Peclet number is let's say greater than 10, what it means is convective flux is 10 times greater than the diffusion flux, which means the problem is convection dominated, and since convection dominated, um, we need to take care of flow. Okay, the way the discretization scheme should have some uh, knowledge of which side the flow is. Okay, so that's where we skip the schemes. Okay, is that what you are
Okay.
asking for?
Yes, sir. And sir, after this, then we consider diffusive flux 0. Then we have to consider this approximation in all the three functions, which like phi p, phi e, and phi w, or else in the two of them we have to find diffusive flux for. Is it like that?
Right. So actually, you no need to consider it as a zero. It's just for simplification we will do it. You can just keep it like that and you can solve it. That's not a problem.
Yes.
Okay.
Okay, sir.
So
Thank you, sir.
if you so actually here what you are doing is this: if you consider diffusion flux to be zero, this whole thing goes to zero. Like you will just remove it. It won't be in your system. Okay. Ax equal to b system, in that the coefficients won't be there. Okay, so let's say you have a equation like like a convection diffusion term. Okay, convection diffusion equation, you know, this thing, right? Like how it will be: dou by dou x times rho u uh, is equal to dou square uh, gamma times phi by dou x square. So let's say this is convection and there is a diffusion, right? So let's say if the Peclet number is greater than 10, and if you are removing diffusion, let's say diffusion is less. Okay, diffusion I am neglecting. Okay, diffusion neglecting means you will just remove it and you solve for this equation. Okay, so at that time the quick scheme applied for this won't come into the picture at all. So quick scheme applied for this will come into the picture. Understood?
Yes, sir. Understood. Thank you, sir.
Does anyone else have any more question? And you have one more question, right? What was that? Quick schemes and time dependent problems, right?
Here's a time integration method that after this.
Yeah. So in time integration method, so we always deal with unsteady flows, right? So the let's say for example, let's say the momentum equation will be like this, is equal to some gradient of pressure, those things. So we always deal with this unsteady part in our equations. So how do you approximate it? So that's where this time integration schemes come. So what people usually do is, that's what so let's say dou phi by dou t is some function, okay, some function of phi, okay. So let's say taking all these things on the other side, it becomes some function of phi. So what you will do is, you will integrate it, right? So you will integrate it like this, of phi dt. Right? So this is how you are going to do this integration is called time integration schemes. That's what they say. So what you can do is, you can simply apply a central differencing or forward differencing in this case, because you know initial condition. From there you need to go step by step. I mean, you need to uh, march in time, right? So what you will do is, you write it something like this: phi at n divided by delta t is equal to some function of phi. Now so this is how you approximate it. You can get it from this form also. You can arrive at the same equation in this from this form also. I'm just giving you uh, uh, like I'm just skipping few steps, okay. You can go back to the lecture and revisit. So what we usually do is, we will write the time integration in this form. So this F is where convection, diffusion, source terms, all those things comes into picture, okay. So this is the unsteady part. So we need to march in time. How we will march in time is, we know the present time step. With that present time step, we need to predict the n plus 1 time step. So in that way, there is there will be one confusion with you, like I have a function x, function f, okay. It is also dependent on phi. Now I have only initial condition. Should I evaluate this at n, or should I evaluate it at n plus 1? So these are the two uh, like two different ways of doing it, like okay. So here, if you evaluate that function at n time step, okay, if you write this, so phi at n plus 1 minus phi at n divided by delta t, if you evaluate it at nth time step, okay, if you evaluate this function at nth time step, then you have only one unknown. What is the unknown? This would be the only unknown. All those things you know. Delta t is you are going to choose it. All those things you will know. This is the only unknown, so you can get at n plus 1 times. So this is called explicit scheme, okay. Similarly, um, if you evaluate that function at the n plus 1th time step, then this is called implicit schemes, okay. Because here this is also unknown, because you don't know the value of phi at n plus 1, and you also don't know the value of phi at n plus 1. So you have lot of unknowns here. So this function is also unknown, this is also unknown. So this only leads to what is called, this will leads to your system of Ax equal to b, okay. So maybe you work out this problem, okay. Say let's say I have dou phi by dou t is equal to, or this is the 1D conduction equation, okay. So let's say dou square by dou x square, or if I put it in this way, alpha, okay. So here I have diffusion term, which is your function phi f of t. This is the time derivative term, okay. Function f of t, this whole thing. This is so what you can do is, you can divide in, you can either solve using explicit, or you can solve using implicit. Here this will have three terms, t of I plus 1. So let's say you discretize using central difference, okay. I and t I minus 1 divided by delta x square. So all these things you should, if you evaluate at n, it becomes explicit. If you evaluate at n plus 1, it becomes implicit. Okay, these are the starting steps of time integration scheme, and there are few more schemes which in which they what they will do is they will we have this term, right? So they will evaluate it um, taking into account n plus so n plus 1 we need, and they can evaluate using n and n minus 1. So they will construct a scheme for time integration, and in such a way that they will take previous to previous time steps values also to find the present time step value. Okay, so there are few more schemes like that, time integration schemes. So is this clear, like what is time integration? Do you have a rough idea about?
Yes, sir. Yes, sir. Understood. Thank you, sir.
So yeah, you apply different discretization scheme to this time derivative, you will get different uh, schemes, and then so that's why only if it is explicit you will end up getting this Ax equal to b form, and then you need to do Gauss-Jacobi, Gauss-Seidel, or whatever the direct or iterative methods you need to solve. But if it is explicit, you no need any solver, no need any solver in the sense the linear system solver, like Gauss elimination, TDMA, or Gauss Seidel. All those things you no need, because there is only one unknown. Let's say for example you take this itself, if it's explicit these things won't be there, and this is equal to t at n plus 1 minus t at n divided by delta t, right? Delta t you will choose, delta x you will choose, n time step you know the values, only one is n plus 1. So you can always write ti at n plus 1 is equal to something which is known value. So you directly get ti at n plus 1, right? But explicit schemes only have that stability issues. That's what we saw there. So for this kind of scheme, you need to make sure that d should be less than half, right? So if you go back to the lectures and take a look, it will be like something like this. You need to make sure it is less than half. If you make sure it is less than half, explicit schemes will give you solution, which does not require any solver. If you don't have that kind of condition, and if you have a, let's say alpha delta t by delta h square is actually greater than half, then you won't be able to use explicit scheme. You need to use implicit. Then you have to solve Ax equal to b, which means you need to have Gauss elimination or Gauss Seidel to solve that system of equation. Okay, so that's the difference between explicit and implicit. You can go back and revise it. So, anyone else have any more questions?
Yeah, understood, sir. Thank you. Sir, and sir, actually, I wanted to ask that, uh, hello, sir?
Yeah, Hussein, I'm listening.
Yes, yes, sir. Sir, I want to ask that with uh, that D is less than or equal to half is for FTCS, right? Forward in time and center in space. That's all
Forward in
right.
time and central in space. Yeah,
Yes,
yeah.
yeah. Because
So
yeah.
for
Thank.
different schemes, this parameter will change. That you can derive it. So one thing what we saw was we saw CFL to be less than or equal to 1. So this thing I derived in the one of my sessions. So you can go back and derive. You can take that as an example, and you can derive this kind of conditions uh, for your scheme. Let's say if you are using different scheme or you are developing your own scheme, let's say you want to come up with the condition for stability, then you can go back and derive it based on it. Okay, this is for FTCS. Yeah.
Yes, sir.
Okay.
Yes, sir. Thank you, sir. Understood.
Sure. Karthikeya?
Hello, sir. Good evening.
Yeah, yeah.
Sir, I have a question. In module 8, sir is saying that they have provided the code. So, is the soft copy of the code has been provided, or we have to write it from the table? It is like from the PPT by our own. This is what I want to ask.
So actually, Karthikeya, if you go back, if you go into NPTEL, there is something at the last called books, right?
Okay.
And there
Yes,
is
sir.
this English book. So
Yes,
if
sir.
you go back, each and every PPT is given in that. So from there you can write yourself.
Okay, means I have to write
Yeah,
it
you
by
have to
looking
write.
at that.
Uh,
Okay, sir, one more question I am having. What is the purpose of ghost cells? Somewhat I understand. In this, are you able to see? The ghost cells are provided for U momentum equation in vertical direction, and in V momentum equation they are provided in horizontal direction. I want to ask, they are provided because the u velocities which are not present from I equals to 1. So actually they are present from I equals to 2. So that's why we are providing ghost cell in u momentum equation, and for the same reason in v momentum equation. This is the reason.
uh, well, it's not the reason. So the
Okay.
reason for using ghost cell is to implement boundary condition.
Okay. Okay.
So there is no reason like I is starting from 2, or there is no such reason. Only reason is to implement boundary condition. So let me give you a simple example. Okay.
Yes.
So
Sure.
let's say this is your domain. Okay.
Yes, sir.
Now if you are, so you will be using finite volume method. So since you are using finite volume method, so you will be given boundary condition at the faces actually face centers, right?
Yes, sir.
So um, have something like this. So let's say, let's talk about lead driven cavity. Okay. So what we have is, we have this part to be let's say u is equal to 1.0 meter per second. Okay.
Yes, sir.
And all other places are no slip, no penetration. So there u comma v is equal to 0. Here also u comma v is equal to 0. Here also u comma v equal to 0, right? Here again v is equal to 0, right? This is the boundary condition we have, right?
Yes, sir.
Now you see, this condition is not applicable for cell center. It is
Okay.
applicable for face centers.
Okay. Yes, sir.
Okay? So we need to use this for face centers,
Okay.
right? So now how do you use it? Okay. So we have a equation. So so you know, uh, like the equation is same for every cell, right? Equation
Yes,
is
sir.
same for every cell. So let's say you are writing it like this. So for simplified manner, I'm just writing, this is not the correct equation. Okay. Let's say this is the equation, is equal to some function. Okay.
Yes, sir.
This is the equation. Now you will apply this for everywhere in the domain, but in the boundary domain you don't have I plus 1. So let's say for this control volume. Okay. For this
Yes, sir.
control volume, you let's write it like this: 1 2 3 4 and 5. Okay. So if you want to write equation for this fifth control volume, how will you write it? U5, it will be u6 minus u5 divided by delta x equal to some function,
Okay. 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 And
right?
we have
But
no six here.
do we have u6 here?
No, sir. That's why. Okay. Okay. That's why we have attached a ghost cell.
That's
Okay.
why. So easier way is to attach a ghost cell. Okay. So if you
Okay.
attach a ghost cell, one more catch is here. So if you attach a ghost cell, you have to use this point, sixth one, right?
Yes, sir.
But we have condition here.
Yes, sir.
We have condition at the face. We don't have condition at the ghost cell center.
Yes, sir.
Now, so how do you implement this condition? So u5 is your unknown. So what you will do is, you will take all other things on the other side. So what you have here is u is equal to 0. So this is 5, this is 6. This place u is equal to 0. And here I have u5. and here I have u6 which is imaginary, which is a ghost cell. Now in order to make this u to be 0, what you have to do is you need to make u6 to be minus of u5. So what happens, this velocity is coming to the face, there is another equal velocity coming to the other face, right? So if you equal this, then what happens, this condition is already satisfied. So what you will do is, so let me complete. What you will do is you will you know this velocity. How do you know this velocity? This velocity is nothing but minus of u5. Okay, so you use this information in the coefficient matrix, and then you will solve that equation. Okay, so how do you get this relation? So this is based on logic I gave you the relation, but if you have some complicated condition, let's say your dou u by dou x is 0 there, okay, this u can be any variable, like if it is a temperature, okay, this temperature you can specify, or you can specify the gradient of temperature, or maybe some heat flux condition will be coming there. So that all those things should be specified at the face, not at the cell center. So if that is the case, how do you do it? So now you have u to be 0 at the east, okay, u east should be 0. So what you could do is you can write u east to be u5 plus u6 divided by 2, which is nothing but linear interpolation. Okay? Okay, so from u5 to u6, if you linearly fit a curve, it will be like this, u5 and u6. So at the cells and like at the faces you need a value. So what you will do, u5 plus u6 equal divided by 2 will be the value at this u east, and now we know u east should be 0, right? So you make this to be 0. Now what happens, u5 plus u6 equal to 0. So what happens, u6 equal to minus u5. Now you simply implement this in the ax equal to b, and you will get the solution. That is the reason we use ghost cell. So if you don't use ghost cell, how will you implement boundary condition? Do you have further question in ghost cell? I will show you one more thing. So do you have further question in ghost cell?
No, sir.
You understood the concept, right? Why do we implement this? So now it will be more clear. So let's say you have a this thing pi, and this is the ghost cell 6. So now you have ue to be 0. Okay, now you have a let's say the equation. Okay, so more rigorous way of implementing a boundary condition is this. So let's say the equation is something like u times u dot n dA is equal to 0. Okay, this is the equation, let's say. So this equation, what you will do, ua at east face minus ua at west face is equal to 0. This is how you will write.
Yes, sir.
Right. So let's say for fifth control volume. Let's say for fifth control volume, how will you write this equation? ua at phi east minus ua at phi west is equal to 0. Right? This is the discretized equation. Now you know u at east is equal to 0. So what you will do, your whole discretization equation changes. So what you will do, the equation simplifies as west is equal to 0. Okay, so you use this equation. Okay, so let's not put equal to 0, you might get confused. Some function of u, this is also some function of u. This is equal to 0, so this is some function of u, this is some function. Some other terms are there in addition to this convection, some other diffusion terms are there. So what happens, your condition reduces to like this. So and then what you will have, you have this phi west, this is phi west. So instead of phi west, what you will write is, you will write say you are doing linear interpolation. Okay, you will write u at phi west to be equal to u a at phi minus u or u a at 4 divided by 2, right? Now
Yes,
you
sir.
will write uh, so there is no area at phi, so actually you will keep this as u phi, and this will be like simply west only. Or let me rewrite this. Sorry. Write as u at phi west, a at phi west. You know area at phi west. U at phi
Yes.
west you need to know. This part you need to know. You have lot of schemes to know that, right? Based on here and there. Like you will write it like u at 5 plus u at 4 divided by 2 times area at phi west, right? Now you have now your equation changes like this. So let's say if you are putting it back, plus u4 divided by phi west is equal to some function of u. Now you will write u5 minus u5 minus u4 is equal to f of u into 2 divided by area of phi
Yeah.
west.
Yes, sir.
So this would be your discretized equation. These are we don't know, right? This equation, so your original equation has changed to this form because of applying boundary condition. This equation you will put it in the Ax equal to b with respect to all other equation, and then you will invert the matrix, and then you get the solution. Okay, so this much complications are there. So you need to derive the each and every step, and you need to understand which flux goes out, and then you need to implement it. But if you see ghost cell, since you have another one more cell, and you are maintaining the boundary condition at the faces, you can apply the original discretized equation itself on the boundary, and you can solve it. So you no need to change the discretized equation at the boundaries. Okay,
Okay.
so that's why we use ghost cell. There is no other advantages of using ghost cell. It's easier to implement the boundary condition. So if you go to some uh, like some uh, softwares, let's say, if you take OpenFOAM for example, so they use this rigorous implementation of this boundary condition. They don't use Gosel. Some softwares they use Gosel. So in fact Gosel is easy to implement, so it's better to use it actually. Okay, so there are different ways of implementing boundary condition. You need to make sure boundary condition is applied at phases, not at the cell center. So that's the
Yes.
reason we have a Gosel.
Okay,
Okay.
sir.
Any more
Okay.
questions?
No, sir. Thank you. Thank you, sir.
So does anyone have any more questions? All right. So if there are no more questions, we are already in the mid of the session. So we will quickly go through what happens in that in this course. Okay. Um, uh, so uh, so you guys should tell me now. So what happens in the course? So at first we dealt with basics of fluid mechanics, right? So we dealt with some coordinate systems, like how to convert different coordinate systems, like cylindrical to spherical, cylindrical to Cartesian. All those things we did because we are going to use it in our conservation equation, right? And then we also saw some vector operations like gradient, divergence, and curl. Like in gradient, what we do, we just convert the scalar field f into a vector field, right? So f is a scalar, so gradient operator is defined like this. It is a vector. So when you multiply these two, you are going to get a vector field. In divergence, what we do, we also multiply two vectors in which the del operator is like this. So you will end up getting a scalar field because these two dot product of two vectors is a scalar. Now again we have one more thing called curl. So we use curl in the verticity equations and all, right? So we also saw curl, and then we saw something called total derivative. So this total derivative is where all the equations have the inertia terms. Like if you check if it's a velocity equation, let's say momentum equation, these things would be velocity. So So this would be already velocity. So this part would be like convective acceleration, this part would be local acceleration, right? So this would be the total acceleration. So this is, and then you will multiply by rho, which becomes m times acceleration, which is equal to all the other forces like pressure gradient. Okay, so basically momentum equation is nothing but F is equal to ma. Okay, and we also saw continuity. So the continuity is very important because all these equations are not continuity, I mean continuum. So continuum approximation is very important because based on that approximation only we derived all those governing equations, right? So continuity, momentum and energy conservation equations are actually derived uh, by considering, by making one of the approximation continuum. What is continuum? It's nothing but uh, fluid is filled everywhere in the domain and every property can be defined everywhere and it is also bounded, right? So uh, and then we saw viscosity. So what is viscosity? um, can anyone tell what is viscosity?
It is a frictional resistance offered by a surface to the flow.
Right, so it's like you can say it is an internal resistance. It's
Yes, sir.
not only at the surface, it will be inside the fluids also, between
In
two
between
fluid
layers,
layers.
yes, sir. The resistance between layers whenever
Right,
a fluid
so
flows.
it is actually internal resistance for the fluid flow. Okay, and then we saw Newtonian and non-Newtonian fluids. Newtonian means it obeys Newton's law of viscosity, which just simply says that shear stress is nothing but with the deformation rate, right? So this is will be the deformation rate. This is stress. Stress is directly depends on the deformation rate. The non-Newtonian fluids doesn't obey that. Okay, and we also saw like scalar and vector fields. All those things are just quick recap of fluid mechanics, and then we came to governing equation. So in governing equation, in easier sense, you can write it like this. So what we basically do is we convert the system equations into a control volume equations. So uh, so system is for a fixed mass, right? You always write it for a fixed mass, right? So like F is equal to ma is for a fixed mass, right? Similarly, so all these equations are for fixed mass. So what you did is you what happens in fluid is you don't have fixed mass, fluid comes and goes out. So what we do is we will approximate as a control volume, and uh, we will convert this system level of equation into a control volume level of equation. For that, what we do is we use something called Reynolds transport theorem. So this converts the this system thing into a control volume and the control surface. So these derivations you can look back. Okay, Reynolds transport theorem. I'm just giving you quickly recapping it. So here the n is extensive property, eta is intensive property. So if you put n is equal to mass, and then eta will become mass by mass because it is a intensive property, like you need to divide it by mass. So then it becomes 1, right? So we know that dm by dt for a system, because it's a fixed mass, the system will be equal to 0, right? So this part will simply become dou rho by dou t at dv plus integral of dou v dot n dA equal to 0. So this will be your mass conservation equation. Similarly, you can put n to be p, to be v, right? You can get a momentum conservation equation. Similarly, you can put energy. Let's say for total energy you need, total energy you can put, and then eta to be specific energy. So you can put these things in this equation and you will end up getting uh, all those governing equations. So we have three governing equations. One is mass, momentum and energy, right? So I'm not writing it because we already wrote a lot of times in this course. We have three equations for any system, for any flow. uh, in our case, okay, we need to satisfy these three equations. So when it becomes incompressible, this so what we have is, we have, before going into incompressibility and all, So what we have is we have 2 3 unknowns here, right? And we have similarly we have u, v, w and p. These are your variables of interest. Here is just temperature is our variable of interest. So what we have is total 5 unknowns we have, right? So if it's become incompressible, we the pressure and we also have density. We forgot density. 6 unknowns. So now density also, usually if it's a gas, it becomes like P is equal to rho RT. All those ideal gas equation comes. Density depends on pressure. All those things will come into picture. So basically, if it's incompressible, that's what we were dealing for this entire course. So what happens? Rho is constant. So one variable has reduced, rho is constant, and P is not dependent on T. So we no need to solve for energy equation. So we just need to solve for mass and momentum equation. So then what we saw was we saw something called vorticity transport equation, right? I am not writing the equation again here. um, so why did we use vorticity transport equation? Can anyone recall it? Vorticity and stream function equation. Why do we have to study that equation? So basically we were telling that
Sir, I think in order to reduce the number of variables, we are using stream functions and vorticity. Like these terms, we are using in order to reduce the number of that variables which are present in the equation.
right. So exactly. So what we have is we have lot of velocity, like we have velocities and pressure u, v, w, and p. Right. We need to solve for 4 unknowns, and we have again 4 equations. Those are all non-linear coupled PDEs. So what we reduced is we reduced it into one equation in terms of vorticity and uh, stream function. So that one equation we will solve for vorticity and stream function, and we will get back velocities and pressure. But remember, this is only for 2D. You need to do it for 2D. Okay, 2D, and I guess you can do it for axisymmetric also, axisymmetric simulations, because stream function is defined for axisymmetric thing. Um, Vorticity would be, I'm not sure. So please check this point. But basically, it is for 2D. If it is a 3D, you can't. You can't do this operation. Okay. So this is all about vorticity and vorticity stream function equation. And then basically, as Karthikeya said, we are trying to reduce the complexity. And then what we did was we did study about little bit about PDE and its classification. So basically the PDEs can be uh, classified based on their order linearity, like if it is a linear or non-linear. It will be classified based on order, and it is also classified based on solution nature. So we saw this part a little bit in detail, like we have uh, basically 3 PDEs: so hyperbolic, parabolic, and elliptic. So we also learned a little bit about characteristics, and can anyone guess why we need to classify this? So I have mentioned it before in lectures also. So what is the reason for us to classify this PDE? Okay,
Well, to apply boundary conditions.
yeah, very good. So one is to apply boundary condition. Okay. So, by understanding the solution nature, you will come to know the characteristics. Right? So, characteristics means you will eventually use it for by getting the boundary conditions. Okay. So, for a PDE, what are the boundary conditions we need to specify, and where we need to specify will be given by the nature of this PDE. So, there are 3 types of PDE: hyperbolic, parabolic, and elliptic. The another is to apply a uh, according to that PDE, you need to apply proper discretization schemes. So this part hasn't been dealt in this course, but I'm just giving you. So the schemes also will differ for different uh, like nature of PD. So this is a little bit advanced CFD. Uh, you can check for hyperbolic PDEs. For hyperbolic PDEs, we have different schemes. The same scheme, if you apply it, you may not end up in getting a proper solution. So that's why it's better to understand what is the nature of the solution, how it behaves. So that part will be given by this. So basically, you will find the discriminant like P del is equal to b square minus 4ac, and based on that you will classify it. And you all know the examples, like hyperbolic is wave equation, parabolic is 1D conduction, and elliptical would be Laplace or Poisson equation. Then what is the next, what we did after this? So after this, what we entered was important part of CFD, which is discretization, right? So what is discretization? So you cannot solve a PDE because it's it is it is complex in nature. You can't solve it by hand. That's why we have to know that we will restrict our expectation to be only in few areas, like where like domain of interest. So let's say this is my area. I no need to know everywhere in this domain. I no need to know everywhere in this domain. So I just need to know only at some points. Like let's say these points I need to know the values. So that values is enough for me. So for that also you need to solve a PDE, but you cannot solve a PDE. So you are discretizing it based on these points. So that's why we were first studied about uh, grids, right? We studied about grids, like structured and unstructured grids we studied, because like how we are going to, what are the domains of domain area of domain we are interested in, we did that. Then what we did, we tried to approximate the derivatives, because at the end you are going to solve the PDEs for those areas of interest. First you are identifying the areas of interest by using by domain decomposition, like your not decomposition, I mean domain discretization, and then for that you are going to apply PDE, and by approximating those derivatives using schemes. For that, what is the main base of those schemes is Taylor series, right? So from Taylor series only we derived all the schemes, and there are few more like polynomial fitting method. All those things are um, we discussed polynomial fitting method to come up with the schemes, right? So basically we found out that for example, let's say you have dou phi by dou x, you can write plus 1 minus I by delta x plus some order will be there. This is called truncation term. So truncation term which gives you the order of the scheme, right? So this is actually forward difference. Similarly, we have backward difference and central difference, right? And what else we did? We also did for dou square phi by dou x square, right? Um, second order derivative. So first order derivative we did uh, order, and then we also did for second order derivative, and there are a few more derivatives like mixed derivatives we did, and for non-uniform grids we need. So if it's a non-uniform grid, then you can't take delta x I to be equal to delta x I plus 1, because delta x varies in every uh, thing. So that's why your equation, your scheme changes a little bit, right? You can stop me anytime if you have any question. In the interest of time, I'm just rushing it. So we also, for each and every so we have the partial derivatives like this, let's say, and dou by dou tau. So we won't be, we can't solve this by hand. So that's why we discretized, we approximated these derivatives and substituted in the equation in order to get simple Ax equal to b system. So once you get Ax equal to b system, you can invert and solve it, because Ax equal to b only we can solve. PDE we can't solve. So that's why we did discretization. To know discretization, where are the points you need interest, that's why we did. After doing this, what we did was, we also, there are few methods of doing this, right? These are finite difference, and what are the other methods of discretization? We have finite volume, which is extensively used in CFD, and we also have finite element. People are actually trying to use finite element also in CFD, uh, but yeah, few softwares like Comsol and all, they use finite element method. They don't use finite volume method. But people always prefer for finite volume method for CFD, just because you can ensure conservation. So that's the reason we go for finite volume, because it's the equation also written for a control volume, and you are also solving for a control volume, which ensures like how much the flux is passing, crossing, the conservativeness it takes. So basically, as we said, so finite volume, we need to take off conservativeness. In addition to that, what we did was, what are the other things we should also make sure. Yes, Karthikeyan.
Sir, just I want to ask, like the code which is given to us is using finite difference method, na sir? The
uh, I'm not sure. So actually they are doing simple algorithm, right? So simple algorithm is actually finite volume method, so the code is also for finite volume method.
okay, okay, sir. Okay.
I believe so. So why do you think it's finite difference?
Because sir, sir said that the code is written in finite difference method. So that's why I was asking like whether it is finite difference method or it is a finite volume method. Uh,
So I'm not sure. I need to go and check. So basically, if the code is written for finite difference, then maybe that is for finite difference.
so
Okay.
just I want to ask like how we can identify like whether it is for finite difference or for finite volume. Is there any if you give us some brief like if you
Right, right. So actually, how do we identify is, basically the coefficients will be different. Okay. So if it's a finite difference, the coefficient would be different. If it's a finite volume, let's say you derive it, like so usually finite volume is uh, from integral form of equations, right? So you will have area terms. So there will be areas, because fluxes are crossing the area. So to identify fluxes, there will be areas. But
okay,
in terms of finite difference, there won't be such areas. It will always be like in terms of delta x and delta y. Okay. So
okay, okay.
that is one way. The other way is you can get from coefficients itself. So here you will write it like ai plus 1, phi I plus 1 plus ai phi I, and ai minus 1 phi I minus 1, something like that you will write it, right? So is
Yes.
equal to b, something like that. There it will be in terms of present cell and east cell, west cell, like that it will be. And these coefficients won't be same. So let's say for a n phi n is equal to b. Okay. So let's say some these are same equation, and if you have this is from finite difference and this is from finite volume. Okay. So if you do like this ai plus 1 will not be necessarily equal to a east. Okay. There will be a difference in the coefficients basically, but it will mostly it will be in terms of ratios, uh, but you can identify from coefficients. And If you have a, and as I said, there will be a area term in every
Okay.
coefficients. So in that
Okay.
way you can find it.
Okay.
So,
Okay.
but okay, so I need to check whether it is finite difference or finite volume. But
Okay.
usually people write for finite volume only. Let's see. Fine.
Okay.
So,
Okay, sir.
yeah, and in finite volume, what we do is we need to take care of conservativeness, boundedness, and transportiveness. So, uh, these are the things we need to take care, which will be it should be taken care by the schemes we use, the finite volume schemes we use. So, that is what we did in finite volume, and then what we did is we also did some error analysis. So, why we need to do error analysis? Because whatever we are dealing with is going to have some error. Okay, because we since we are approximating a derivative, there is a truncation error, right? And, there is a round of error, because what you are going to do is for every addition, subtraction, multiplication or division, what you will do is you will round off at, let's say, some 15 digits or 16 digits. Even the computer round off step. So these errors, you should make sure that as simulation runs, these errors shouldn't accumulate and it shouldn't blow up. Okay, like it, the errors shouldn't grow. Okay, should not grow. So that's why what we did was we did some error analysis where we used something called von Neumann stability analysis. This is used for linear equations, as I said. Um, uh, so von Neumann stability analysis we use to identify what should be my delta t and delta x uh, get stable solution. And if you get a stable solution, it will be convergence. And we also saw something called Lax Equivalence Theorem, which tells that um, if you have a if you ensure stability on a uh, conserved scheme, then you are going to have convergence will be free, right? It will automatically be converged. So that theorem we saw, and so once our all these things are ready, like the discretization, all those things were ready, we used we used it for in addition, we also did for time integration. So time integration schemes we did, as we discussed earlier in this class. So since we have unsteady terms in our equation, we have time integration schemes also we discussed. So and then what we did, we integrated all these together to solve our mass, momentum, and energy, mass and momentum equation, right? So integrated all these to solve mass and momentum equation. How did we solve? We have few methods like Mach, simple C, simple R. So uh, uh, all these methods have something in common. So if you notice, all these methods are like prediction and correction. So what we did in simple was first one is to predict velocity, right? First one is to predict velocity, and then predict the pressure, and then we will correct the velocity, right? So this is what we did in simple. So this is what the lid driven cavity also is doing. If you go through the code, you will predict the velocity, you will predict the pressure, and then based on the predicted pressure and predicted velocity, you will correct the velocity such so that this will satisfy conservation of mass, and all three, because you predicted from momentum only. So conservation of mass and momentum. So that is our ultimate aim. For every delta t, you need to satisfy mass and momentum conservation, and you do it in a sequential manner, like simple algorithm, predicting and correcting. So, and we also touched a little bit about turbulence, right? So I'm not going into turbulence right now because we don't have enough time. Um, but what we essentially gave is very little introduction about turbulence. Turbulence is a vast area. You cannot. There should be a separate course to have basics of turbulence. Here we just touched a little bit like what is turbulence and why we are doing it. So basically in turbulence what we saw was, so I would like to take 2 minutes extra time so that I can finish it. So in turbulence, what we saw was we saw something called Reynolds stress coming into picture. So why Reynolds stress is coming? Because we know turbulence. Turbulence is nothing but it is the flow field is chaotic and unsteady and chaotic, right? So the flow field will keep on oscillating. So that's why what we do is any instantaneous velocity is actually decomposed into a mean velocity and then a fluctuating quantity, right? This is fluctuating quantity and this is mean velocity. So whatever we do is we solve for mean velocity, but the fluctuating component comes only when the flow is turbulence, right? So if you plug in this equation in the momentum equation, you will have this extra term called Reynolds stress, which is also unknown. So you will have some 6 extra unknowns in addition to 4 unknowns, u velocities and pressure. In addition to it, we have 6 extra unknowns, um, which leads to something called closure problem, right? So you need to somehow come up with some other equations to um, find this 6 unknowns. So we have a lot of methods, like one is Reynolds averaged Navier-Stokes equation, one is LES, and another is DNS. DNS is nothing but it doesn't have any Reynolds stresses because it solves for very small uh, delta x and delta t. Okay, so at this small delta x and delta t, there won't be any fluctuation quantity. Whatever quantity you find is the instantaneous velocity or pressure. So but that scale is very very small that you can't discretize and solve it for it is very difficult. It is in still in the research stage. You can't do it in industry for industry purposes. But in trans we have something called k epsilon, k omega model, and in addition lot of other models also. LES is like you won't resolve for, so here you fully resolve all the eddies. So you know turbulence is going to have eddies. You will fully not fully resolve, like you won't resolve at all eddies, like you will use these models to find the average velocity. LES you will resolve for larger eddies, and because it's called large eddy simulation, right? So you will resolve for larger eddies, and smaller eddies you will just model it using this k epsilon and k omega, like k epsilon and k omega, how we model the same thing we will model in LES. So that's what we briefly touched turbulence. It's a vast subject, and then what we did was is to finally coming to the linear equations. Like system of linear equation is what we are going to solve. So whatever we did is to come up with this system Ax equal to b. Once you come up with this system, we need to solve it. So that's what we solved. That's what we saw finally, is to find this. Is how you are going to solve this Ax equal to b. So as discussed, there's going to be two methods, right? There is going to be direct and there's going to be iterative. So direct methods, what we did was we used Gauss elimination, right? Gauss elimination, TDMA. There are a lot of uh, direct methods, and LU decomposition. All those things are there. Similarly, we also have um, Gauss Jacobi, Gauss Seidel. All these are iterative methods. For every iteration, it changes. So um, based on iterative method, we will solve this Ax equal to b. Finally, we have to get x. X is nothing but A inverse b. So to get this thing, we use these solvers like direct and iterative solvers. And we also saw that sometimes this matrix becomes very tough to invert. So that's because it is an ill-conditioned system. So if it's an ill-conditioned system, we need to convert into a well-conditioned system. How do we do it is using preconditioners. So that's where we use preconditioners. Preconditioners is just multiplying a matrix to that Ax equal to b system. So let's say you have a Ax equal to b system and your preconditioner is m. Okay, so you will multiply m inverse Ax or m Ax, I'm not sure. So m inverse b, and then you will solve this x is equal to and then you will solve and get the x. So this equation will be well conditioned such a way. That's why you used preconditioner. Okay, So how do you find whether it is ill conditioned or well conditioned? Based on the condition number of A, right? Condition number of A, you all know it's a row sum norm of this condition. So if the condition is very large, okay, it doesn't have any number, but if it is large like 1000, 2000, or like for a small change in delta, for small change in one of the elements, there's a large variation in the solution. That's what it's called ill conditioned system. So that you will find it using condition number of A. If the condition number of very large, then it's a ill conditioned system. Then you will multiply by preconditioners. So those things happens when you solve a equation. So when you solve a set of equations, either in commercial softwares, then you might end up having diverging solutions. So those are because of this uh, properties of the matrix. That's why we need to be so there will be inbuilt preconditioners. We need to use those preconditioners to have it. Or you need to ensure diagonal dominance. If you ensure diagonal dominance, these problems doesn't come, right? So that is one thing. So finally, we all did lid driven cavity problem, right? So lid driven cavity, um, we did using simple algorithm. So what I would say is I've also explained you something called quasi-ratio, which is easy because simple does for staggered grid, right? So it displaces the control volume. For you it will be like this. For V there will be one more control volume. For pressure there will be one more control volume. But what I thought was it's a quasi-ratio method in my previous two sessions. So what you try to do is, since you did simple algorithm using those program, you can go through the quasi-ratio method and you can implement the same thing, but this is for collocated mesh. So it is not for staggered, it is for collocated mesh, and you can see how the results is. Okay, so these things you can try it on your own. um, yeah, in addition we also have few more test cases like this lid driven cavity is a test case, like similarly forward stairs, facing step, all those things you can try with the same program, I would say. So same program you can try, or you can write your own program. Only thing is the domain will become different and you need to apply proper boundary condition. So at the end of the day, um, uh, a solution algorithm is going to give you a solution, but your input should be correct. So how you need to make sure that your boundary condition is right. So for whatever the solution, wherever you solve it, you write your own program or you solve it in your software, no problem. But you need to ensure that you are giving correct boundary condition, and you need to ensure you are solving for correct equation. Okay, correct equation in the sense with proper terms. Like some equations might have eliminated diffusion term, some equation might have eliminated convection term. So you should understand your problem, your domain, and you should have a proper boundary condition. You should know what should be your boundary condition, and you should also solve the correct equation. If you make sure these things are right, the solution algorithm will give you a proper solution. Okay, so the solution algorithms, when I say it's like simple, so these are segregated approach. There is something called um, uh, segregated, and what is the other one? We have coupled approach, right? So in coupled we solve it together, we don't predict and correct, we just solve it together as a vector system. Coupled approach, solve for rho u and rho u. So you can check about this in my previous sessions also. So the solution algorithm is going to give you correct solution, but you need to ensure that you are giving correct boundary conditions and you are solving for correct equations. Okay, and initial condition, some problem might depend on initial condition, like unsteady problems might depend on initial condition, but if it's a steady state problem, uh, if you make sure that initial condition is more related to more um, uh, near to steady state, then your solution algorithm will give you solutions. I mean it achieves convergence in a very fast manner. If it is far from steady state, then it will take some time to converge. Okay, so that's all from my side. So if you have any questions, you can ask. By this, I will stop this session. Okay. All right, guys. Thank you.